Okay, so mostly here we wanted to review, okay, our work energy theorem stuff. Now, when we look at question number 1, it says a box with this mass is lifted above ground level. What kind of energy is being changed in that question? Potential. All right, so the work being done is changing the potential energy in question number 1. Okay, so give them a mark if they have work as a change in energy or work as a change in potential energy or something like that. Okay, if they have EF minus EI somewhere, that would also be good. All right. Now, the things we know the mass, we know the height, and we always know gravity. Now, since it was on the ground, what was its initial energy? 0. All right. So its initial energy was 0, which means the change in its energy is whatever the final energy is. Whoops. You're right. I changed the quiz and forgot to change my answers. So let's do this way. Okay, we'll still give the mark for the work as a change in potential energy part. Okay, so they still get a mark for that. Except this time we know the work. Now we need to know how high it gets. Okay, sorry. So we know then that the work is going to be equal to the final potential energy. Now, if they wrote minus EI, that's fine. Okay, but that means we have to get to this point. That work is equal to m times g times h. All right, and we have to manipulate for h, because that's what we're being asked to find. All right, so HF is going to equal then, okay, the potential energy, or the work, we'll say work because that's what the question has. Okay, work over mass times gravity. Give them a mark if they got to that point. Oh, I forgot to give you marks for givens. Sorry, marks for givens. Okay, mass 8.5. Okay, and work 183 joules. Sorry, 1 mark for givens. Now, so if they showed this or they showed their numbers plugged in, whichever, okay, is that mark there? So 9.81 times 8.5. All right, and that should still give us 1.6 meters, right? Yeah. All right. No, is it? Okay, so I changed everything and really messed it all up. Okay, hang on here. All right, so 2.2 we'll say. If they have 2.19, that's fine. Okay, so there we go. Final mark is for the answer. Okay, so there's 4 marks there. 1 for givens, 1 for works of change in energy, 1 for manipulation or plugging, and 1 for the answer. What if what? Then it's wrong. Yeah, if you don't have units, it's wrong. Okay. All right, and then the second question. Soccer ball with a mass of 0.75 kilograms is kicked from rest to a speed of 21 meters per second. So, givens. 0.75 kilograms for mass. Okay, final velocity or final speed, 21 meters per second. Okay, we're looking for the amount of work done. Give them a mark for that. What kind of energy is being changed here? Kinetic, because the speed is increasing. All right. Does it have any kinetic energy initially? No, because it says it's kicked from rest. So we could actually write VI as 0 as another given here. All right. So work is a change in energy, which is the final kinetic energy minus the initial kinetic energy, which was 0. All right. So we can just eliminate that part. Okay. So we're looking for the amount of work done. So work equals 1/2 mv squared. Give them a mark for that. Okay, or if they just went straight to plugging in their numbers, 1 times 0.75 times 21 squared. Okay. Okay, should give us 165.4 joules. Then it's wrong. Okay, they gotta have the right units. No, that's out of 3. 1 for the givens, 1 for 1/2 mv squared here, and 1 for the answer. 3 marks. So the whole thing is out of 7. Yeah, that's fine. Okay, questions on any of those? Oh, that's fine. Okay, so mark out a 7, put it in the box, guys. All right, so over the last little while here, guys, we've been doing a lot better in general on our lab reports. Okay, so we need to listen really carefully on this one because this is another big opportunity to keep boosting that part of our grade, okay, or keep it where it is if that's the case for some of you. Okay, it's a relatively straightforward lab. Okay, where we're just going to be essentially testing the effect of force and distance on work. Okay, so what we're going to have here is a setup like you see in the picture. Okay, where we're going to have a couple of desk legs, okay, here and here, and we're going to have a rubber band strung around them, and we're going to pull them with a spring scale. Okay, that's what this thing is. All right, and we're going to measure the force on the spring scale and the distance on the ruler on the floor. Okay, everybody with me so far? All right. Work is, and we can calculate that not just with a change in energy, but also by multiplying force and distance. So that's the part we're going to be looking at today, okay, is the force times distance part. We will probably also do a lab that will start out exactly like this, except we'll put a car in the rubber band, okay, and see if the work we do translates into kinetic energy for the car. All right, a little bit later on, but that'll, okay, so that'll be the kind of change in energy parts, 2 separate experiments. So the thing we're doing here, how can you determine the amount of work done on an object? Well, we could calculate the change in energy, or we could multiply force times distance. Essentially, those are the 2 things. So in the design here, we want to identify our manipulated, responding, and controlled variables. Okay, now the way you're doing this is we are going to be pulling the rubber band to certain distances. So what thing are we selecting? We're selecting distance, okay, and we're measuring the resulting force required. Everybody follow? Okay, and the resulting force is directly related to the amount of force times distance equals work. Okay, so we kind of have 2 responding variables. Okay, one of them is going to be used to calculate the other. All right, but obviously the manipulated variable is that thing that we are choosing. Now, the distances may not end up being the ones listed here. Okay, the reason I say that is because it's how far you can effectively pull the rubber band is very much related to how far apart the desk legs are and what length of rubber band you get. I think they're all close to the same length, okay, but you may get one that's slightly longer. So what you need to do when you're setting this up, and this is the most important thing, is, okay, pull your rubber band with the spring scale, okay, and the spring scales look like this. Okay. They look like this. All right. Now, unfortunately, this one, okay, is different than the one that you have. Okay. Mr. Dickey and I, when we moved to this school, ordered spring scales that had newtons on them. Okay. We got boxes that have pictures of spring scales with newtons on them. In the box are spring scales with ounces and grams. We said, these are not what we ordered. Northwest Scientific says, yes, they are. And we said, no, the boxes are what we ordered. What's in the box is not what we ordered. You got what you ordered, so they wouldn't give our money back. Anyway, okay, here's the good news. It's not that hard to convert the reading in grams to newtons. Okay, so whatever your scale reads, divide that number by 100 to get the force in newtons. Okay, so in this example, okay, the force would be 4 newtons. So you can see here if this tab, okay, the tab was down here at 400 grams, that's 4 newtons. Everybody all right with that? Okay, it's pretty easy conversion, right? We can all handle that. Agreed? Okay. All right, so that's what we're going to be doing. Again, these distances, guys, in meters, okay? Make sure your distance is in meters. Why is that important? Right, it's got to be in meters because the units for joules for work and energy are kilogram meters squared per second squared. Centimeters will not get you the right units. So please make sure your units are in meters when you're filling in your chart. And again, okay, for picking which distances you're going to use, this is what you're going to do. Put the rubber band across the 2 desk legs and then pull on the scale until you get to about well, not quite to the end, okay? Not quite maxed out, but just maybe to, instead of 2,000 grams, maybe to about 1,800 grams. All right? However far that is, okay, record the force and the distance and make that your last number. All right? So if you pulled it, let's say 15 centimeters, okay, you'd write in here 0.15 meters and 18 newtons. All right? Then pick some other distances that are fairly even between 15 and 0 for your other distances. Pull to those distances and measure. Everyone follow? Okay. Reason being is if we just pick distances, you might get to the point where you've maxed out the scale and you're not at the end of all your distances yet. Okay? Does that make sense? So do your maximum one first by pulling this pretty much as far as it will go. Okay? Recording that distance and then do distances for the rest. Okay, we're not really changing the experiment that way. We're just making sure that it works and we get good data. Questions on that part? Right. Yeah, we're doing it in here. It's easy. You're just gonna, okay. Now you can't do it the way they showed on the diagram here, which they showed it all on. Well, they don't really show exactly that it's the same desk, but you're going to need to use two different desks. All right. So you're going to put the two desks. Okay. So if you're looking here at these legs between Jason and Brenn's desk here. Okay. So if we move them about, so they're about 10 centimeters apart. Okay. Then put this thing in there and make sure that it's taut. All right. Not tight, just taut, so it's not hanging loose. Everybody follow? That's a good starting point. You can measure from there. All right. You will put the meter stick in between. Make sure that the meter stick is sitting right on where the rubber band is. Now, obviously, the rubber band is going to have a little bit of separation, okay, when it's sitting in between. So it'll look like this. Okay. Put the ruler right smack in the middle because you're going to hook both sides. Okay, with the spring scale. Make sure that when you're pulling, you've hooked both sides. Everyone follow? All right, so that'll help you to get your data. So you will need to make a chart like the one I've shown you here, okay, with your distances and your resulting forces. Okay, that part shouldn't be too tough. Okay, you're going to build a graph, okay, of force versus distance when you have all of that done. All right, so our hypothesis, okay, we need to generate a hypothesis that explains how, with those materials that we have there, okay, we can calculate the work done on an object. Now, if we know the formula for work, that should be relatively straightforward. If we're going to be using a force-distance graph, okay, there may also be some instructions in here that help you to figure that out. Okay, so in the analysis part, okay, you're going to calculate the area beneath the line on the force-distance graph, okay, using the equation for a triangle, obviously, half the base times the height, okay, so half of the maximum force exerted, blah, 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 okay. So the area here is going to be our average force multiplied by our distance moved. Okay, so essentially it's force times distance. Okay, and then for question number 2, what does the area under the force distance graph represent, and how do you know? Right, that's the most important question, obviously. Okay, yeah, I want to look at your math and I want to see that you're able to do that, but I know that you can calculate the area of a triangle. Okay, my big concern is what does that represent, and how do you know? Okay, I'm going to want some justification on how you know whatever it is. Okay, and then have your conclusion evaluation. Remember, you don't have to do the class discussion questions. Okay, we will talk about those when I hand them back. All right, is everybody pretty clear on how this is going to work? Now, there are two different sets of spring scales. There are 500 gram spring scales and there are 2,000 gram spring scales. Please grab the 2,000 gram spring scales. The boxes are clearly labeled. Okay, so make sure you get the 2,000, because if you get the 500, you'll be like 1 centimeter, 2 centimeters, 3 centimeters, because it'll max out right away. Okay, so get the 2,000 gram ones. They will work best. I will bring out some meter sticks here in a minute. Okay, there are lots of spring scales, so you can probably go in partners. Okay, and then you're set. Maddie, question? Well, I think on this chart I had, so not including 0, 1, 2, 3, 4, 5, 6. Okay, so 6 distances, guys. All right, so I'm going to want 6 points on the graph, 7 if you count that 0, 0 is going to be one of your points. All right, everybody follow there. That way we get good data on our graph. Okay. All right, so rubber bands. Oh, lab safety. Nobody does this. Because if you do, I will hold you down and I will smack you repeatedly with the rubber band. Okay? No shooting the rubber bands at each other, please. Okay, like I said, guys, these are labeled. If the boxes are turned upside down, just turn them over, and you'll be able to tell which one you've got. Okay, let's get going on that, guys. You got the rest of the class to work on that. Recommendation for you before you start pulling on the rubber band with the spring scale. I would put at least one group member sitting on the desks, because if you don't, the desks will slide. Okay, just a couple more tips here for the analysis, because there's been a few questions about it. All right, big thing here, guys, is that you do all the stuff it asks in question number 1. I want to see those calculations done. All right. Now, there was some confusion here about the second part where it's talking about area equals average force exerted multiplied by distance moved, and it says area equals F_av times d. And I've had a bunch of people say, well, Mr. Coder, isn't it a triangle? Shouldn't I divide by 2? And the answer is you are, if you are using the average force, because the average force is somewhere between 0 and your maximum force. In fact, it's right in the middle of the two. Would that be dividing your height by 2? Is that base times height divided by 2? Yeah. Okay? So that's what they're saying there. They're saying calculate the area of the triangle. That's fine. Okay? Either way is fine. Whichever way you do it, you're going to get the area of that triangle, and I will accept it as correct. Okay? But if there was some confusion, we're saying the same thing in different ways. All right? Does everyone follow me there? All right? But remember, it's your justification in number 2 that is most important. Right? I don't want to see a simple one-sentence answer for question number 2. I want some explanation and some justification for your reasoning there in question number 2. Okay. Also remember, guys, that we chose the distances. Okay, and that affected 2 things. How many responding variables should you have? 2. Okay, 2 things are affected by us choosing different distances to pull the rubber band to. All right, now they are dependent on each other, okay, but there are 2 responding variables. Make sure you have them both. Okay, controlled variables, there's lots of those. Right, you shouldn't have any trouble getting 3 or 4 of those. Okay, and they're little things like, remember I told you that you needed to have some people sitting on the desks, because if the desks moved, what happens to the distance between the legs? It shortens or widens, and then your rubber band doesn't have the same amount of tension in it. That can affect your experiment. All right, so things like that. Okay, all those little things. All right, so due date for that, guys, is December 9th. Okay, that's Monday, so it's not that far off, but by the same token, this lab's not really that much work. All right, so make sure you've got it all done for then.